So if you look at this, you can see that the generalized system, that's for physical system, and generalized control dynamics, they are very similar. They are very similar. All right. So we have U here too, and this is BU, and we have BC, UC, and there's a UC here. Okay. And my UC here will be my KCW, and that's and here is the UC here can be something else. So now, from one degree of freedom become generalized system, and that's the dynamics you can use for it. Any questions? I try to avoid as much as I can about the mathematics. What I try to do is, if I can use some physical explanations for those equations, I would just rather use just some physical way to explain my mathematics. Okay. You have any question about these two side-by-side comparisons? No, right? Okay, the control interact with the system via this. Let me just turn off this guy so you can use that. So my U will be like my YC minus FY. Now I have a gain FY. And UC will be equal to Y, will be that's equal to CDW. There's a CDW here. Because I have a KCW here, then I generalize become a CDW. So I have another gain called CD. I have another gain called F. So I have two more design parameters I can use, rather than just this KCW. I have a CDW that's related to my KC, but I generalize it. So to do that, and I have this. This CD is from this CD here, right? And this is W because Y equals CDW, and that's my CDW here. U equals YC minus FY, and this FY is a CDW, so F CDW, and then YC is a CD WC, and that's I have a WC here. Okay, so this is just a way I generalize it so that I can do it for multiple degree freedoms. That's all I do. There's nothing fancy here. Any questions? Because we are going to get heavy in math. All right. If you don't have any questions, let us look at the overall system matrix equations. Look at this one here. I have M and MC, that's my cross loop. That's my cross loop system matrix equations. I have zeta, zeta C, and KKC. They don't couple together. Before I U, and UC, they are all independent. But they will couple through my U and UC. If you look at this, if my U is equal to CD, C, WC minus F, CDW, my UC will be equal to CDW, then you can begin to see their coupling. All right? If you sub this together in there and move those WC and W into left-hand side, then your couple becomes this. Because there's no couple in mass matrix, there's no couple in the damping matrix, there's a couple now in stiffness matrix. Agree? Any problem? No? You do? I think it's easy just to plug the B there to get the left-hand side, right? I think so. You need to listen carefully, otherwise the next homework you may have some difficulty to do the next homework. Okay, now let's just do a little bit more so that you have some feeling about it. Okay. So you see that's equal to B 0 and 0 BC and times CDC W C minus F CD W, and then this is C D W, right? If I time like that, then I will be able to do this equal to B 0 BC times a matrix CDC, and then minus F CD, then CDC times W and WC, and this is CD 0, right? Wait, makes sense? And if I do this, this equal to minus BC BF CD, then BCDC, then BC CD, then 0 WC. Agree? Okay. Yeah, true. So I move this to the left hand side and add this one back to right? Okay? Right, this to move, this term is that term, and this term is moved to the left hand side become plus. That means K plus B F C D, and this is minus B C D, and this is minus B C D, right? DC. Okay. So the question is, the system is stable or not? This closed system is stable. This closed system. Now we know that if this closed loop system will be stable, MC, both of them be positive definite. Because M is positive definite from physical system. MC is my virtual MC. I can make them to be positive definite. No problem. So this matrix is positive definite. All right. So we have closed loop system, the mass, stiffness, and damping matrices. And this 0, 0 and 0, 0 C, we can make them to be positive, semi-positive definite, or positive definite. If zeta, original system, the zeta is positive definite, the zeta C, this zeta C, we can make them to be positive definite. No problem. Right? So, this M0 and zeta MC, no problem. We can make them to be positive definite. 0, 0 and zeta C and 0, 0 C, there's no problem. We can make them at least semi-positive definite. If my physical system zeta is positive definite, then my zeta C will be positive definite because that's I assign it. If I have freedom to assign it, I'd rather use the positive definite matrix. Agree? All right. Now only the last one. This one. This one we have to be positive definite. If this one, the last one, the stiffness matrix, the combined stiffness matrix, this is the combined stiffness matrix. If this combined stiffness matrix is positive definite, then we know that the whole system is stable. At least stable. May not be asymptotically stable, but is stable. Right? Agree? Any argument? Any questions? No? All right. Now, what is the problem now? What is the problem? Do we have any problem? No? So, now the KT, we call KT. T means total, right? The overall system is K plus B F CD minus B CDC and minus B CD and then KC. All right? We have to make them this one to be hopefully not or equal to 0, right? Minimum. Agree? To make sure this is positive definite, what is the first things we have to do? What do you mean the positive definite? Positive definite matrix, the matrix cell has to be what? And this can be a midterm problem, you know? For a matrix to be positive definite, the matrix must be symmetrics. Right? So this we must be symmetric first. That's the first requirement. The matrix must be matrix before we can talk about positive definite or not. But now we know that we have a degree of freedom only what? This is our we can choose it. This we can choose it.